So, part two. Whoops. Relative extrema. If we're looking for relative extrema, we have to first look for critical values because those are places that it can change. And so if we're looking for critical values, we want to find out. Now notice I said just on the interval 0 to 2 pi. Why do you suppose I would do that? What's that? Okay, so there's sine. What does that mean? Okay, we're going to use the unit circle. Very good. But why would I narrow it from 0 to 2 pi? Why would I do that? Yeah. Yeah, because wouldn't sine just keep on going? And so wouldn't we have tons of extrema? We'd be sitting there all day, right? And so I narrowed it down so that we didn't have to do that. And so what's obviously the first thing we're going to do? Find the derivative. And why do we find the derivative? Just because that's the thing we've been doing for the last month? Yeah. Because I want to know where it can change from increasing to decreasing. Okay, and that only happens at critical values. So what is the derivative of 1/2 x?
1/2.
Yeah, that wasn't a trick question. It was just 1/2. Minus, what's the derivative of sine? Cosine. And then you write down the angle, which is x. Then you take the derivative of the angle, which is 1, and so no big deal, right? And so I want to find out, please do not forget to look where it's undefined. If you did that on the next problem that I assigned for today, you probably weren't going to get a whole lot of information out of it, right? If you forgot to look for undefined. How about cosine? We spent a lot of time graphing some of the trigonometry. That's another one. It's basically sine shifted over 90 degrees, right? It just keeps on going on and on. Are there any problems with that? Any times that that's undefined? Nope. How about 1/2? We're pretty good with 1/2 too, right? So do I have to find any places this one's undefined? No, because there aren't any, right? So now what I have to do is find out, where does that slope have a chance of being horizontal? We said there are no places the slope would be vertical. And so that's what we did by saying there's no undefined. Now let's go ahead and find out, well, where is this going to equal 0? There's a step of algebra here that could save you some issues. The easiest way to do it is just add the cosine over to the other side. So then you have everything's positive, right? And how is it that you take trig away from the angle? How do you break it apart? Arc, right? Arc, whatever it is, right? It could be arc secant, arc tangent, whatever. But here we want arc cosine. So cosine to the negative 1 to that side, cosine to the negative 1 to that side. What happens on the left side with the cosine to the negative 1 and the cosine? Cancel. So it's saying my angle, right? It's still an angle, x, equals arc cosine of 1/2, which really translated says, whenever you have arc anything, think of it as where is cosine 1/2. And we'll do it up here. So where is cosine 1/2? Okay, so I've been told pi over 3, which is way up here or down here? Right here? So you think that's where cosine is 1/2? I see that some of you are cheating and looking at your unit circles instead of actually trying to figure out where it is. Cosine's the x value, and it is the smaller of the two. So it happens where was the first one? Pi over 3. Okay, does it happen again? Where? Where's that? Which quadrant is that in? Are you sure? How are you so positive? She may have looked at the unit circle. Okay. Okay. So 5 pi over 3 is another one. Are there any other places? Well, technically, if I didn't stop you at 2 pi, you'd have to go back up to pi over 3 and state it again and keep going around this thing. But I said only go from 0 to 2 pi. Okay. So, what are our intervals? This is the most important part on this one, really. What are your intervals? Yes. Yes, up front. Person in the purple shirt. What are the intervals that I have to check for increasing and decreasing? The person up front was close, but they said negative infinity.
I meant,
Yeah, you start at 0,
I meant
0 to pi over 3. And why is that? Who can state why I'm looking at that interval? Because, yes. Okay, we are going around in a circle. That was, I thought there might be more there. Yes. Okay. 0 is where I'm asking you to start, yeah, basically. And so start there. In the first place it can do what is pi over 3? Change. And let's face it, it's sine, so it stands a pretty good chance, right? There's no guarantee, but it stands a pretty good chance that it will change at pi over 3. And so then we want to say, well, from pi over 3, there's another interval here that it has to do the same thing the whole time. And you would go to, yeah, 5 pi over 3, because that's the next place that it can change direction. But basically, from 0 to pi over 3, this thing either has to increase or decrease. It has no choice. It can't change. Yes? Oh, yes. It's not infinity? No, just 2 pi. Right. Because if you said infinity, that would actually be wrong because it could change an infinite number of times by the same time it gets to infinity. Because this just keeps going around. Okay, so normally with trig, they will narrow it down a little bit. Otherwise, if they don't, you just have to do like we did on the chalkboards over there. You have to say, oh, it's pi plus, 180k or pi k or whatever. So, who remembers from yesterday what we should do now? We have beautiful places, and we have these intervals. Well, what do we have them for? Yes. Yes, we need to pick some kind of test number. Can we all feasibly pick a different test number and still come up with the same answer? Yes. Exactly, as long as it's in the right interval. Exactly. So we're going from 0 to pi over 3, correct? I can choose anything I want. Is pi over 4 a good choice? Let's do it. So we're going to try pi over 4. Well, what do you do with that then?
put it in your derivative,
Why derivative?
because otherwise it would just give you out 0.
To give you a y.
Well, it would give me the y value, yes. Okay, so put pi over 4, basically I should not have chose green. Put pi over 4 right there is what you're saying. So it ends up being 1/2 minus cosine at pi over 4. So this testing is a little bit harder. Well, what is cosine at pi over 4? Square root of 2 over 2. So it's 1/2 minus the square root of 2 over 2. Well, basically, the square root of 2 is bigger than 1, right? It's 1.414-ish. So it's 1 minus something that's bigger than 1. The same denominator, right? Or you could say this is 0.5 and this one's about 0.707. And so if you subtract, you're going to get negative. And notice, did I sit here and get a common denominator and do all this work to find out exactly what it was? No. Why? Because, yeah, I don't care, basically. It's not because I didn't need to. It's because I don't care. I just want to know if it's positive or negative. Okay? So now the next interval I'll do in blue. Well, blue's a bad choice, isn't it? I'll do in red up here. From pi over 3 all the way around. Why is everybody shouting pi? Okay. Well, whatever. I personally would have chose pi over 2 because then it would have just been 0. But anyways, you said pi. That works. Nope, you said pi. Nice try. I don't think so. So you chose, it still works, it doesn't matter. All right, so you chose pi. Cosine at pi, that's over here, right, is? Yeah, so it's 1/2 minus a negative 1. Positive. Now, pi over 2 would have been easier because cosine there is 0. Another good choice would have been 3 pi over 2 because it's also 0. But anyways, it's positive anyways. And let's do the last one in, I guess, black. We have to go 5 pi over 3 just to there. So you notice these intervals are not even, are they? That one in the middle is huge, but the two on the outside are not very big at all. And so what's a good choice? What? I heard 7 pi over yawn. That's what I heard. 7 pi over 4, that'll work. So in other words, right up very close to it, right? And what is cosine there? Yeah, it's square root of 2 over 2. Didn't we already do that? Isn't that the exact same thing we did for pi over 4? Because isn't cosine going to be the same there and there? Because it's the x value. And so it's once again going to be negative. So we have all these lovely negatives, positives, and weird different colored numbers there. What does it all mean? From 0 to pi over 3, what is happening the entire time? So it is doing what? Decreasing. In this huge gap here of pi over 3 to 5 pi over 3, it is increasing. From 5 pi over 3 to 7 pi, it is decreasing. So are they extrema at pi over 3 and 5 pi over 3? Are they extrema? Yes. Do we know absolute, relative, anything like that? Not necessarily, but we do know for a fact that they are extrema. And in fact, we know this one is at the very least a relative. It's going down and up, right? So it's a relative min at the very least at x equals pi over 3. And over here at the very least, it's a relative max at 5 pi over 3. We don't even know the y value because, and you have to watch out. If I ask for critical points, then you better go get the y value. If I ask for critical values, then just give me x. If I ask for critical points, I'm asking for a point. And if you just tell me pi over 3, is that a point? No, that's an x value of a point. Go find the y. And how do you do that? Substitute it back into the original. Now, if I ask for a critical value, which is normally what I'll do, because let's face it, we can all substitute stuff back in and get a y value. All I want is the x, if I ask for just that. Yes? Question?
Yeah.
I said at a very minimum it's relative. It could be absolute. But it has to be an extrema at the very least. And the lowest level of extrema is a relative extrema. Absolute is when you find out, is it the biggest or smallest overall? Yes. Well, it's I know it's at minimum. That's the worst it could be, is that. And if you want to know, well, once again, I'm not going to use this, so I don't know why it's there. It looks nice, I guess. 2 pi is right here. I'm going to give you a little sketch here. So based on that graph, so if I were to give you that graph, what would you now like to tell me about pi over 3 and 5 pi over 3? They're absolutes, aren't they? Okay, because that is the actual graph of the original. And here's your pi over 3 is right about here. It's about a third of the way to pi, right? That we now know. And is it actually from 0 to pi over 3, is it decreasing? And then does it increase for a very, very long period of time? From here all the way to here, which we know is 5 pi over 3, right? It is increasing the whole way, and then it does actually go decreasing, as we found out in our intervals. The key I'm trying to give you here is you don't need to see these graphs to be able to do this. Are they helpful? Yeah. Does it help you understand? Probably. Yes. Exactly. That's what I was saying. What can you conclude from the graph at this point? You won't be asked to. Unless I say, here's an interval, I'll give you something simple and say, find out the absolutes and something like that. But remember, when I give you an interval, what's the places people normally forget to check? They find all the critical values. Where do they forget to check? Endpoints. Okay, because if you have, this isn't this problem, but you could have a very simple graph that does something like that. Well, there's your absolute max. Where's your absolute min? At an endpoint, right? So don't forget to check them. Because they could be absolutes if you have endpoints. If I ask you for the whole graph, it doesn't matter. Here's your problem, huh? How many extrema did you come up with? 3? Okay, 3 critical points. How many extrema? So one of them wasn't? Oh. Seems like people might be paying attention here. Very good. That is correct, by the way. If you got 3 extrema, you are slightly incorrect because there is an asymptote involved in this problem. And the graph was probably very strange. That's why I chose this one for you. So how did you start your problem? Derivative, and how do you take the derivative of this? Quotient. Very good. Quotient is bottom, which is top. Yep. And then derivative of the bottom. And then again, kind of watch out for that. All over the bottom squared, so it's x squared squared, so it's x to the 4th. And so you kind of clean it up. So this is 4x to the 5th. So it's a very good, minus 2x. Why is it minus 2x? Yep, distribute your negative. Yep. Yeah, that's another way of saying yes. You have to because you have to distribute it through. Did some of you leave it this way and try and solve? You could have. Okay. So I'm going to clean this up. Then I am going to erase some. So make sure that you keep up with me here. And you should have all this written down already. You know, but I see some people writing feverishly, meaning that they didn't have any of this written down. 4x to the 5th minus 2x to the 5th is 2x to the 5th minus 2x all over x to the 4th. I would do one more thing if I were you. I would have factored a x out of the top. You don't have to. Whoops. You want to? All right. We can do that too. Now, why would I factor that out? Yes. Okay, not actually why I did it, but you could do that. I did it so I could do this. Do you have to? No, but you can. And so now this is our nicely cleaned up derivative. Now what? Why? Yeah, looking for places that it might be undefined or places that so basically I'm looking for a vertical tangent and horizontal tangent is what I'm looking for. What am I going to do with this though? When I'm solving and setting equal to 0, what do you almost always do with that denominator? Yeah, you just multiply it up to here. So the nice thing is and now you're really starting to understand why I really don't care about radicals in the denominator anymore. Because you're going to deal with them separately anyways. Just leave them down there. And then you got to solve this. Well, you divide by the 2. You add the 1. Take the 4th root. And so x equals, very good, plus minus 1. Because it's an even root. And I probably should have put the 4 there. But I'm trying to go fast because, like I said, you should have this written down. But that's, so some of you said you had 3 critical values. That's only 2. So at the bottom equal to 0, which very nicely, yeah, let's say that's 0. So your critical values are all right there, right? Yes, you can do the intervals. Go ahead, fire away. For those of you wondering if why that factoring that x out didn't matter is you were going to get 0 anyways. You're going to get 0 as a critical value anyways in that problem, and that will always happen. So if you don't simplify, you're still going to get enough information. It's just you'll get some duplicates. Okay? And that's okay. You know, it doesn't matter. So what do we got here? What's a good choice, maybe?
-10.
Negative 10.
-0.5.
Yeah, unfortunately, there's no good choice there. And probably 10. Now, 10's an easy choice because it's so easy to square, so easy to cube, so easy to do a lot of things to. And the nice thing about 10 is if you take it to a big power, it gets huge in a hurry. Either positive or negative, so it's a nice one. So now I've got all these numbers. What should I do with them?
Put them in the derivative.
Can I put them just in here?
No.
No, because I need that denominator, right? So I can't just put it there. But I can substitute it in there and there. Now I'm not going to spend my time doing all this math. So it's negative 10. You take it to the fourth, that's going to be very huge. Positive minus 1, still very huge. Positive times a positive is still positive over
Negative.
a negative. Because negative 10 cubed is negative. So overall, maybe we'll do overall in green, negative. So what'd you find out? We'll just go through these quick. Negative half it was, positive, negative, positive. Do not assume it will always alternate. Because remember, critical values are places it
Possibly.
can or possibly can change. If it always alternated, we wouldn't have to do this testing. We would find the first one and then just alternate it. Okay? So what that means, in just by looking at it, that at x equal negative 1, it's basically decreasing then increasing, right? This one's going down, this one's going back up. So at first glance, it would seem like this is a relative min. At first glance, here, I'm going to put them up here because I think they're getting a little low for people in the back there. This one's going up and down. So at first glance, this is a relative max. And you'll find out why I keep saying that. And this is a relative min at your first guess. But as some of you mentioned, you have to watch out. Watch out for discontinuities. That's any holes, any asymptotes, anything like that. So you have to look back at the original. And this is why we spend so much time talking about asymptotes. You have a denominator. And it's not going anywhere. There's no holes that I can cross off and all of a sudden I don't have a denominator. It's going to be there. And so you set your bottom equal to 0. X equals 0 is an asymptote. There is no horizontal or slant. Who can tell me why? Yeah? Perfect. The top is more than one bigger. So what dominates? As x gets big, the top pretty much gets out of control, right? You can't, the bottom can't control it enough. If it's only one bigger, the bottom tries really hard, and it does for quite a while. But here, yeah, there's just nothing else. And when you actually look at the graph, you probably realize, whoa, what's going on? All right? And so basically what happens, we know we have at least that. And that's it. And what happens is, okay, I don't know the actual values, all right? So just, something like that. I think it's a little bit more symmetric than what I have, but you get the idea. So which one of these gets eliminated?
0.
Yeah. Why? Because that value
Is it this?
is an asymptote. Does it change direction, though? To the left of it, it is increasing. To the left of it, it is.
Decreasing.
So did it do what it was supposed to do? Was it a place it could? Yeah, but it's not there. Okay, so it can't. But it still was a possible location. Exactly, if it was there, it would have. Yes? What do you mean, what they are? Say that again.
Like on the previous page, or even before, we
Uh-huh.
had the actual points that were relative min or relative max. How can we just look at those values right there?
Oh, you mean like right here? This is at negative 1. Right there.
They're the same.
Well, that's where it could change direction. That was one of your critical values. That's where it could actually change. So that's and this is at x equals 1. This one was a possible change. 0 was a possible place for it to change, but it's not actually there because it's an asymptote. And so it is not a relative max at x equals 0. It's an asymptote. Okay, once it's an asymptote, it's done. It's nothing else. Now, truly, these are not relative. They are absolute. But if you don't see the graph, all we know is at the very worst, they're relative. Yes? Well, we'll definitely get some more logarithm stuff. Not on this set, but it's just the asymptotes with logarithms and exponentials are a little different. And so we will look at them, but exponentials and logarithmics are kind of weird. They don't often give extrema.
So we don't need to know any of that kind of stuff before it's coming up, right?
Well, I may ask you to do it to see if you find critical values.
What's the one that wanted to give an example?
Yeah, right there. Number 12, right over there on the chalkboard. And 11 and 13. Okay, look at these are what the graphs look like. Are there extrema on that? I mean, there's an absolute right here, but you're not going to get that from doing any of the work. That's why most of these people that had these logarithm problems from before, look at what they're not getting a whole lot. Okay, because of what the graphs look like. Good question.